Our first speaker is Christina, who will be talking remotely about efficiently exploiting model structures in network causal inference with or without knowledge of the network. So since this is an online talk, if you have any questions, just speak up saying, I have a question. I will bring the mic to you so that the speaker can hear your question. Okay. Christina, please go ahead.
Great. Thank you so much, Suvik. And I'm really bummed I couldn't be there in person. However, I will be coming in person very soon. So I'll be coming in person in the end of October for the next workshop, and I'll be staying to the end of the program. So I'm really excited to meet many of you then soon. And so I'm excited to tell you about this work on causal inference with networks. And so hopefully it'll be, I hope to kind of introduce a new and interesting problem to all of you. And I think it's a space where there's a lot of space for contribution in terms of thinking about how to incorporate network structure. All right, so let me just start with a application. So of course, the last few years have all been, COVID's been on the top of our minds, and the CDC put out statistics on the effect of mask wearing. So how much do you reduce your risk if you wear a mask? How much do you reduce your risk if people around you wear a mask? And you can think, how is that statistic actually computed? You can imagine one way to try to estimate it is to look at observational data of people wearing who in the population who wear masks and some people who don't, measure the health outcomes of whether people get COVID or not, and to just estimate the average difference in the COVID testing results between mask wearing and not mask wearing people. But of course, there's actually two issues with this this approach. First of all, there could be confounding if we're using observational data. So people who choose to wear masks may actually have different susceptibility and pre-existing conditions. And so when you're measuring the difference in health outcomes between mask wearing and not mask wearing behavior, people, you may not actually be estimating the effect of the mask wearing. You might be estimating differences in the populations wearing masks versus not. So this is a reason why oftentimes we turn to using randomized experiments when we're trying to estimate something causal to try to get around this confounding issue. However, there's still an issue here that even when if we were to use a randomized experiment to try to estimate the effect of mask wearing, and the challenge is that actually your individual outcomes, your health outcomes, is affected not only by your own action of whether you wore a mask or not, but also by whether the people around you wore a mask or not. This is what we're going to refer to as network interference. So when the treatment assigned to your network actually affects your outcome. I'm going to give one more example, a motivating example. Suppose I am LinkedIn and I want to evaluate a new social media newsfeed algorithm. So I'm trying to decide between the new proposed newsfeed algorithm and my status quo. So what I could do is I could run a randomized experiment, randomly assign a fraction of the users to this new algorithm, and then compare the performance on some metrics such as user engagement or activity, and compare the performance of the new algorithm versus the status quo algorithm. However, again, we run into this network interference issue where the individual's behavior on the social media platform have an influence on each other. So whether, even if I'm put in the control group and I got my status quo, the status quo algorithm, my experience on the platform depends will change if my neighbor was assigned to the new treatment, because they will maybe generating different content for my newsfeed. So let me step back first and set up what is going to be the causal inference task. What's the thing we're going to try to estimate, and how does it have to do with the network? So first of all, what we're going to want to do is evaluate the effect of a proposed treatment versus control on a population of size n, which is going to be connected via some known network. For the purposes of this talk, we're going to assume that the network is static. But actually a very interesting question is to actually think about a setting with dynamic networks as well. So I'm going to posit a potential outcomes function y, which is a function which specifies all hypothetical outcomes. It's a function that maps from the vector of all treatment assignments to outcomes over individuals. So in particular, we're going to consider binary setting where an individual either gets treatment or control. So the treatment vector is in 0, 1 to the n, and it maps to an outcome over all the n individuals. So that's r to the n. So the causal estimand, the thing we want to estimate, is going to be the total treatment effect. It's the difference between the outcomes of the average outcomes of the population under the vector where you fully treat everyone, that's the all ones vector, and the vector where nobody is treated, the all zeros vector. And this is an estimand that is particularly relevant for settings such as the one I described in LinkedIn, where the goal of running the experiment is to decide whether you commit to this new treatment or the new proposed algorithm or revert to the status quo algorithm. And the challenge of causal inference is that we only observe data from a single treatment effector. So imagine I run a single experiment, and now that experiment is, I have to choose a treatment vector to assign for that experiment. But given the observation from that one experiment, I want to figure out how to estimate these causal estimands. So we're going to need a key assumption, and to contrast it with the assumption that's often used in the literature, the classical work often assumes what's called the stable unit treatment value assumption. This is an assumption that imposes that an individual's outcome only depends on the individual.
There is a question in the audience. Sorry to interrupt.
Oh, okay, yes.
Yeah, so I figure this might be something you're going to explain in a bit, but just to be clear, are we assuming that the potential outcomes function is deterministic? Or
Yes, I'm going to assume that it's deterministic. It's actually very easy to add independent noise. Actually something that would be very interesting to think about extensions would be a setting where potential outcomes function actually could be could be time varying if you're actually in a dynamic setting. But here we're going to assume a deterministic potential outcome function. Yeah.
Okay.
Independent noise is easy to add. Correlated noise is harder. Yeah.
Okay. Thanks a lot. Yeah.
Thanks. Good question. So we're gonna want to, of course, relax this classical assumption on stable unit treatment value assumption. Instead, we'll assume what's called neighborhood interference. So neighborhood interference, an individual's outcome only depends on the treatment neighborhood, meaning that if I have, so here I'm using y sub I to index the potential outcomes of individual I. Individual I's outcome under two treatment vectors z and z prime is going to be the same as long as the assignments of treatments to the neighborhood of I, so that's denoted by script ni, for these two vectors is the same. So if the neighborhood assignments are the same, then the outcome should be the same. And so it allows you to reduce the, simplify the potential outcomes function to be only a function of the assignments to the neighbors. And here I'm going to consider this neighborhood and script n to include the individual I itself. So the neighborhood is going to be myself and my neighbors. And furthermore, we'll be considering the experimental randomized experiment setting where treatments are going to be assigned randomly to avoid confounding between the treatment and the individual's characteristics. And when I say randomized design, that's going to refer to the distribution of the treatment vector Z. So in particular here, we're going to, again, consider a potential outcomes function, which is deterministic. So the only thing that's random here is going to be with respect to the randomness in Z, yeah, again, the treatment vector Z is the only thing that's random, not the function itself. So to, I guess, also set up what is a standard classical A/B test that might be run under the classical SUTVA assumption. The natural thing to do is to take an individual, that's the individual here, and randomly assign the individual to treatment or control. And under SUTVA, again, the outcome only depends on this individual's assignment. So if I want to estimate this total treatment effect, a very natural estimator is to use the difference in means estimator. The difference in means estimator simply takes the empirical mean of the outcomes of all individuals assigned to treatment, that's group A, and subtracts the average outcomes of all individuals assigned to group B, that's the control. That's a natural thing to do, and you can see that because we're randomizing the treatments, assignments, and because of the stable unit treatment value assumption, then indeed the difference in means estimator is unbiased and it's a efficient estimator for the total treatment effect. But what happens if you have network interference? So under network interference, the individual's outcome now depends on its neighborhood. And now the total treatment effect estimate, you should think of it as the average population outcome under two hypothetical scenarios, one setting when all of individuals are assigned to treatment and the other when all individuals are assigned to control. And the data that we're actually collecting from our A/B test, again, if we randomly assign individuals to treatment or control, is going to be the outcome of that individual under whatever happens to be the assignment of its neighborhood. So even if I assign individual I to treatment, it could be that it has other neighbors that were assigned to control. And even if I assigned I to control, it could have had neighbors that were assigned to treatment. And as a result, the observation you collect may be neither of the values that are in the estimand you want to estimate. So it might not match either of the outcomes under fully treated or fully controlled. So again, naively using a difference in means estimate, you can see that it will, you can easily construct scenarios in which it incurs significant bias. And so a question we're going to be answering and asking is, how do we use data collected from such an A/B test to estimate total treatment effect under interference? So I'll just pause here and see if there's any questions. Great. So to kind of first tell a natural baseline that you could that we'll kind of compare against. So if I do Bernoulli design, meaning every individual is independently assigned to treatment with probability P, I could use what's called an Horvitz-Thompson estimator. It's really an inverse propensity or inverse probability weighted estimator, where for each individual I weight its outcome by this difference between the ratios of the this ratio here is the indicator function of if the individual and its neighborhood are all assigned to treatment, divided by the probability of that event, minus the indicator function if the individual and its neighborhood is assigned to control, divided by the probability of that event as well. However, you can already see that this estimator may not be that stable, or it may not perform very well because the probabilities in these denominators are actually really small if my degree is high. So in particular, the variance under Bernoulli design of this estimator scales, the main thing to focus on is it scales like 1 over n times p to the d, where d is the degree of let's say the degree of the graph. So for a uniform degree graph. So here, again, the costly part is that this variance scales exponentially in the degree of the graph. So again, the question is whether we can do better. And in particular, what we'll discuss today is we'll present a new way of measuring the complexity of the model, which will then allow us to construct estimators for which the variance actually scales exponentially in that new complexity measure rather than the degree of the graph. Okay, so a quick comment on what the literature looks like. There's kind of two approaches to this space. One is non-parametric approaches that focus on using clever randomized design, but they depend heavily on the graph being clusterable. So for example, if your graph is fully disconnected, then a natural thing to do is you just randomize each of these clusters independently. And then instead your estimator scales with 1 over the number of clusters rather than 1 over the number of individuals. Another thing you could do if your graph is not clusterable is that you can construct a clustering for your graph. So here, if I can, for example, choose cluster centers that are kind of nicely spread apart, and then assign every individual to the cluster center that's closest to it. And then given such a clustering, I can then randomize over these clusters. It can be computationally complex, and not all randomized experimental platforms are set up to run cluster randomized design. But if you could, you can, again, define the Horvitz-Thompson estimator under such a cluster randomized design. And a beautiful work by Johan Ugander and his student actually showed that if you have a kappa restricted growth graph, meaning that the neighborhood size does not grow too fast, if you use this randomized cluster randomized design, then you get a variance which again, the part to focus on is that scales as 1 over n times p, and most notably, it no longer scales exponentially with the degree in terms of the exponent of p. So this is the kind of result and the gain that we would like to get. However, without the cost of having to run a complex randomized design, and maybe without having to make restrictions on the graph structure beyond the degree. Another approach is to take a parametric approach that essentially the most common model is to assume a linear model with respect to known features, and then you just reduce it to regression. You can extend it beyond linear models and use machine learning approaches as well. The limitations that you need to have a fairly simple model class. So you need a lot more data than the parameters to identify the model. And then the number of data points you have is only the number of individuals in your population. So it means that the number of parameters has to be significantly smaller. So it doesn't allow for full heterogeneity over your population. Furthermore, most of these approaches assume what's called anonymous interference, that the model does not depend, my potential outcomes does not depend on the identity of individual treated, but only on the number of individuals treated. And it can be very fragile to model misspecification. Furthermore, all of these solutions, they require either not exact knowledge of the network or at least approximate knowledge of the network. So what we'll look at today is how do we exploit model structure, and how does that allow us to then, in some settings, remove the requirement of having knowledge of the network, and in general, construct estimators where the performance is going to depend on an appropriate notion of the model structure. So to introduce the model we'll look at, again, we'll first observe that because I'm in the treatment vector z is binary, we can express the potential outcomes function as a polynomial in z, where here all I'm doing is writing here I'm summing over all subsets of the neighborhood. AIS is the outcome of individual I when exactly set S is treated. And then this products here is the indicator function. It's expressing the indicator function of if set S is treated and the complement of S is not treated. But as you can see from this expression, that the polynomial degree of the potential outcomes model is always going to be bounded by the degree of the graph, the graph degree of the size of its neighborhood. So a natural way to then measure kind of complexity of this model would be to measure it with the polynomial degree of the model. So it could be a much simpler model in which the degree of this potential outcomes function is significantly smaller than the degree of the graph. And so if you had a degree beta polynomial potential outcomes model, then we can express our potential outcomes function by only summing over subsets of size bounded by beta. So the number of parameters in the model at large is still scales as n times roughly d to the beta, because for each individual I, it has its own coefficients in this model, this coefficient C, I, comma, S. And for each subset S, that's going to be roughly d to the beta, or there are roughly d to the beta subsets, since you're choosing sets of size beta out of a neighborhood size of d. To kind of motivate this, one example that motivates this setting of low degree polynomial, or you can also think of it as low order interactions, because our polynomial is a polynomial of it's over a binary vector. So an example that can motivate it is if I have an individual with a very large neighborhood, has many friends, but amongst that friendship group, there could be subcommunities. So in particular, for example, I have, my family, that's one group, one subcommunity could be my high school friends, or my college friends, or my colleagues, and each of these would be separate subcommunities that are connected within, but not connected across. And it's plausible that my potential outcomes could be additive across these subgroups, but the function that governs the effect on me within a subgroup is not necessarily additive. So it could be because I know that individuals within the same subgroup kind of share information, then if a few of my individuals are treated, it may not, the kind of effect on me may not be separately independent or additive. And so in this example, the polynomial degree would be bounded at most by the size of any of these subcommunities, which could be smaller again than the large degree. Another model, which is a specific setting of our model, is when beta equals 1. So you can also think of it as the linear setting, or we refer to it as the heterogeneous additive network effect setting, because when beta equals 1, you can write your potential outcomes function as simply a sum over these. So here, the first term is the baseline effect. It's whether or not I'm treated, this is the outcome that's always there. And then if I'm treated ZI, then there's an additive effect to CII. And for each one of my neighbors K that is treated, that's indicated by ZK, then there's an additive effect to CIK on me. And so you can again visualize this model using in either matrix vector notation on the left or graph notation on the right, where on the right-hand side, the self edges, the weight on the self edges is the direct effect of me being treated on myself. The weight on the edge from me to another individual is the effect that my treatment has on that individual. And the weight marked on the node itself is the baseline effect, the effect, the outcome that is not affected by whether I'm treated or not. And so if I treat a set of individuals, I mark them as red, and I also mark all of their outgoing edges as red as well. So some nice properties about even the simplest additive model is that it does allow for full heterogeneity in these coefficients. The coefficients can be positive or negative. The number of coefficients can be as large as the number of edges. So it's definitely larger than the number of possible measurements. And it's very easy to add mean zero independent measurement noise as well to the potential outcomes function. And that doesn't really change any of the results. Okay, so I guess the question is going to be, how do we exploit this type of structure? I'll call it low order interaction structure. And what we do is we'll present new estimators whose performance is characterized by the new complexity measure. So in particular, this polynomial degree, which we'll denote by beta, is again always bounded by the degree of the graph. And so what we'll expect is that the variance of our estimators, so our estimators will be unbiased, and the variance is going to scale as 1 over n times p to the beta rather than p to the d. And we'll present results under two types of experimental designs. The first one I'm going to call staggered rollout design. It's a richer experimental setup where you can take measurements over multiple time steps. And the richer experimental setup actually allows us to enable graph agnostic estimators. So estimators that do not require knowledge of the graph at all. The second setup is a more classical experimental setup where I have a Bernoulli design, a single measurement. And the results here are going to allow for randomized design where the treatments are non-uniform, but it does require knowledge of the graph. So let me first tell you about our first set of results. So consider an experimental design where you have where you're rolling out the treatment in multiple periods of time. And this is actually, rolling out your treatment in multiple periods over time is actually already used in practice, because oftentimes, even if I want to run an experiment with, say, 15% of the population, I still want to be cautious and, first treat 1%, then 2%, 5%, 7%, 10%, 12%, just to make sure along the process of my my treatment plan that, nothing goes wrong if there's potential risks. And so in particular, we do impose a monotonicity that the treatments are nested. Once an individual is treated, they remain treated through the period, and the within each of the periods, the assignments are assigned according to Bernoulli design. So conditional Bernoulli design, because conditioned on you not having been treated before, then you're independently assigned treatment or not in each subsequent stage. So what we show is that if the potential outcomes model has a polynomial degree of beta, then without requiring knowledge of the network, we propose an estimator, which is unbiased under the staggered rollout Bernoulli design, that has variance scaling as this quantity here. Again, the main thing you should pay attention to is that the exponent now depends on beta rather than the degree d. And so indeed, it means that if I have a much simpler model with stronger structure, then we can get significantly better results than if I were to ignore that structure or not particularly exploit it. So the kind of key aha is that this ability to take multiple measurements via staggered rollout design actually enables estimation of this total treatment effect without knowledge of the network. And the key insight is that you can actually reduce it to polynomial interpolation. So if I have a beta degree polynomial potential outcomes model and a Bernoulli randomized design, the average outcome of the outcomes of the population is going to be a beta degree polynomial with respect to the treatment fraction P. So here I've just written that the expected value of the average outcomes over the whole population under Bernoulli P is going to be again a beta degree polynomial in P. And so the key the key insight is that the total treatment effect is simply the difference between this polynomial evaluated at 1 and 0. And if we can implement a staggered rollout design, we can get estimates for this polynomial at multiple levels of this treatment fraction P. And so if I have a beta degree polynomial, I minimally need beta plus 1 different treatment. I need to observe this function at beta plus 1 different treatment levels in order to learn the polynomial. And so the estimator is not particularly interesting to show because really it's just literally using polynomial interpolation and applying it to the estimates, to the empirical measurements of the average population average outcomes. But I will tell you the example for the specific case of the linear setting. It's kind of it's very intuitive and very simple to explain. So in the linear setting, it reduces the setting of this notion of staggered rollout now for a linear setting, because the degree is 1, I only need 2 measurements. So in particular, the most reasonable kind of setting is to assume that I have these knowledge of average baselines. So before the experiment, I just estimate what the population average of the kind of status quo is, and then I run a single experiment. And having access to that previous average baselines gives me that extra data point that I need for this result. So with an estimate of this average baseline for any randomized design such that the marginal treatment probability is equal, then the estimator we propose is the following one. You take the average population outcome of your experiment, subtract off the average baseline, and scale it by 1/p. This is an estimator that's unbiased for any network under our model. And again, the thing to observe from this estimator is that nowhere did we need to use knowledge of the network to compute it. And under Bernoulli design, the variance scales as 1 over p times n, which is the best that you could expect because we're treating p individuals out of n. And so I'll give you a visual picture of what the result is. The total treatment effect under this model is just the sum of the weighted edges. So sum of the weights over all the edges. And because again, the outcomes, the outcomes are the sum of the nodes plus the edge weights, and you want to subtract off the outcomes under control, which are all the nodes. And so the total treatment effect is nothing but the sum of the weights over all the edges. And if you treat an individual, I'm referring it to is it activates an outgoing edge, or you mark it by red. And the measurement that you're taking is, so the kind of action taken, the treatment affects outgoing edges. The measurements are on incoming edges. So the measurements I take are sums of my incoming red colored edges plus the node value itself. And the estimator that we construct, we can show that it's just the sum of all these red activated edges. Now it becomes more clear to see that, even though the measurements are taking the sums of the incoming edges, by just averaging all the outcomes together and subtracting off the average baselines, which are the node values, what we do is we get we're essentially computing the sum of all the red edges, so all the outgoing edges of treated individuals, which we're going to refer to the influence of an individual as the sum of its outgoing edges. So this kind of mapping allows us to show that this network interference setting is equivalent to thinking about a setting without network interference, a survey sampling setting where I have individuals, and this parameter L just denotes their influence on the network. That's the sum of the outgoing edges. And for every individual, so whereas the estimator on the left, what it effectively does is it sums up the values of these influence terms for all treated individuals. And so simply by randomly selecting a subset of the individuals to treat uniformly at random, we get a uniform estimate of we're computing the empirical average of a uniformly selected subset of the population. And so the simple insight is that given these baseline estimates, this network causal inference really is easy as estimating a population mean. So once you do the reduction, then it's easy to show unbiasedness. You can actually compute the variance for other designs beyond Bernoulli and ask which randomized design does better. And furthermore, the dependence on the network was very minimal. So you can even have a fully dense network as long as the influence of any individual is bounded. We did run some experiments that I won't really dwell on, but I'll show you a few pictures. The key, I guess the one thing I want to comment is we compared our estimator against a regression estimator using OLS, as well as difference in means estimators. This is the results on the additive network effect setting where beta equals 1. Our estimator is the one in blue. So what I'm plotting is the relative bias of the estimator. The shaded region is the confidence, or actually is the standard deviation, the empirical standard deviation. And the plot on the left shows what we're varying the population size. The plot in the middle, we're varying the relative magnitude of the direct effects versus the indirect effects. So how much of the effect is coming from the network. And on the right, we're varying the treatment budget. And in all of the plots, you can see that our estimator, the blue one, really does the best. It's the only one that's unbiased. And furthermore, the variance is not very high. The second set of plots is under a degree 2 model. So here, our estimator is still the only one that's unbiased. Its variance is a little higher. And under certain parameter settings, it's comparable to one of the least squares estimators as well. So in the last few minutes, I'll tell you a little bit about our result in the second setup under Bernoulli design. Under Bernoulli design, we are able to present an estimator that allows for non-uniform treatment, but it does require knowledge of the graph. I think the value of allowing for non-uniform treatment is that it allows you to extend it to observational settings where you believe you could estimate these treatment probabilities and impose some unconfoundedness assumptions. Then it implies that the results actually directly extend to an observational setup as well, a limited observational setup. So here, again, I'll present the intuition in the linear model. So here, recall we have our treatments that go on outgoing edges. You can think of that as selecting columns of this matrix. Again, this matrix is our matrix of unknown parameters. And the measurements are on the incoming edges. So the measurements are row sums of the selected columns. And so again, the thing we want to estimate is the sum of all the entries in this matrix that are unknown. So the estimator we propose looks like this. There's a term on the right in the inner term looks a little bit like inverse probability weights, but this sum here is non-standard where I'm going to multiply the outcome of an individual by the sum of all these inverse probability weights of all its neighborhood. But we can show this estimator is unbiased, and indeed the variance scales as 1 over n times p. So again, in the linear setting, this is the best this is actually best we can expect. And we can extend it to a polynomial model. It looks and the estimator looks just slightly more complicated, but again, you're multiplying each of the outcomes by a function now, which is a sum of all the subsets of the neighborhood of some, again, a quantity that looks kind of like an inverse probability weights. And the estimator is indeed equivalent to the Horvitz-Thompson estimator, the fully general estimator, if our degree is large, if beta is larger than the degree of the graph. So in particular, if we don't put any constraints, this does reduce to the most general estimator as well. And we can show that this estimator is also unbiased, and indeed the variance of this estimator scales as 1 over n times p to the beta. So again, the main kind of gain is you can see that if beta is significantly smaller than the degree, then we show that the kind of the exponential part of the dependence on the variance, instead of scaling with the degree of the graph, scales with the complexity, this new model complexity that we're proposing. So we do also some experiments comparing our estimator again against ordinary least squares. Also a difference means estimators. We get very similar looking results where our estimator is in the one in blue. In this setting, the variance is it is a little higher than the OLS estimators. So the OLS estimators are the purple and the red estimators. Those have significantly smaller variance, but have some bias. And so if your population size is large enough, then the fact that our estimator is unbiased will end up being still lead to lower mean squared error. So yeah, I'll wrap it up with a few minutes for questions. So in conclusion, we show new estimators that exploit the structure of these potential outcomes model to estimate the total treatment effect under network interference. And we characterize the complexity of these of the potential outcomes model with a low polynomial degree, which you can think of as low order interactions amongst the neighborhood. And furthermore, if we have staggered rollout designs, so a more richer experimental setup where we can take multiple measurements at different treatment levels, it does enable fully graph agnostic estimators that don't require knowledge of the network at all. And furthermore, we can extend to some settings of unconfounded observational settings if you have knowledge of the network. And there are many open questions in this space. I think you can ask, how do you construct the best estimator for general randomized designs, or even can you optimize the randomized design if you had knowledge of the graph structure and you had the ability to? There's actually some very interesting work by Stefan Wager at Stanford with his student, looking at a more restrictive model than we look at, but they actually impose a Graphon generative model on the graph and show that if the Graphon has a low rank structure, they can actually use the low rank structure to construct a more efficient estimator that has reduced variance when the degree of the graph could be large. So I think there's definitely a lot of interesting questions around there for optimally using network structure if you had it. And also interesting would be, how do you extend these beyond just neighborhood models? Can we optimally incorporate covariates, handle unobserved confounders, or also compute valid and efficient confidence intervals? So I think this last point of how do you show central limit theorem style results for a graph setting where the outcomes are correlated because of the graph structure is also a very interesting question. Great, and I'm happy to take questions.
Questions?
Hi, Christina. Thanks so much for the great talk. I'm wondering, so you mentioned at some point about going to the observational setting, right? In that case, would you then need to assume that even if it's an observational setting, the assignments to the individual vertices are independent, or can they actually be correlated depending on the network structure?
Yeah. So what we can handle is, for example, suppose what I'm allowed to do is I'm not actually able to assign treatment, but I can encourage treatment. So I can run an experiment where I can maybe I can actually, no, I can offer treatment, but an individual has to decide whether to follow through or not, meaning that I can randomize over the offer of the treatment, but I cannot control if an individual takes it or not. And so subsequently, whether an individual actually takes the treatment is a function both of whether I offered it as well as whether they choose to take it. So if it's the case that it could be that individuals' probability of whether they would adopt the treatment if it was offered to them, it could be a function of their their covariate, so, or not even whether observed or uncovariate, so their type. So and that type could be observed, could be unobserved. That's a setting that we can handle. The reason why that is because since we're randomizing the offer, that randomization still gives enough independence, but the probability that an individual takes a treatment or not could be different amongst different individuals, and that probability could be correlated to whether or not they, their type. Because of that, I mean, but that's a particular setting we can map to a non-uniform Bernoulli treatment setting. So there's some kinds of, so main thing is that we have to assume that conditioned on some observed features that we can control for, that subsequently the treatments are independent from anything we don't condition on. So it is there is an unconfoundedness assumption we need for the observational setting, but it's not as restrictive as randomized experiment.
Other questions?
I have a quick question. I was wondering, how do you know it's causal relationship, not say correlation relationship?
That's where we heavily use the randomization part of it, because the randomized, because we're actually assigning the treatments randomly, it breaks it means that any differences we see are truly due to because we're assigning the treatments randomly, there's not variation on the treatments being selectively assigned to certain groups rather than others. And so it allows us to then kind of translate the inference result to a causal one. But that's why if we want to make any conclusions like that on observational data, we would need additional assumptions that once we condition on observed covariates, that then there is subsequently there is independence between the treatments and the outcomes.
Other questions? Okay, if not, let's thank Christina again for the great talk.
Thanks, and I look forward to see you all soon.
You want to set